Parsing, parsing, syntax analysis, or syntactic analysis, is the process of analyzing a string of symbols, either in natural language, computer languages, or data structures, conforming to the rules of a formal grammar. The term parsing comes from Latin pars orationis, meaning part of speech. The term has slightly different meanings in different branches of linguistics and computer science. Traditional sentence parsing is often performed as a method of understanding the exact meaning of a sentence or word, sometimes with the aid of devices such as sentence diagrams. It usually emphasizes the importance of grammatical divisions, such as subject and predicate. Within computational linguistics, the term is used to refer to the formal analysis by a computer of a sentence or other string of words into its constituents, resulting in a parse tree showing their syntactic relation to each other, which may also contain semantic and other information p-values. Some parsing algorithms may generate a parse forest or list of parse trees for a syntactically ambiguous input. The term is also used in psycholinguistics when describing language comprehension. In this context, parsing refers to the way that human beings analyze a sentence or phrase in spoken language or text in terms of grammatical constituents, identifying the parts of speech, syntactic relations, etc. This term is especially common when discussing what linguistic cues help speakers to interpret garden path sentences. Within computer science, the term is used in the analysis of computer languages, referring to the syntactic analysis of the input code into its component parts in order to facilitate the writing of compilers and interpreters. The term may also be used to describe a split or separation. Human languages, traditional methods. The traditional grammatical exercise of parsing, sometimes known as clause analysis, involves breaking down a text into its component parts of speech with an explanation of the form, function, and syntactic relationship of each part. This is determined in large part from study of the language's conjugations and declensions, which can be quite intricate for heavily inflected languages. To parse a phrase such as "man bites dog" involves noting that the singular noun man is the subject of the sentence. The verb bites is the third person singular of the present tense of the verb to bite, and the singular noun dog is the object of the sentence. Techniques such as sentence diagrams are sometimes used to indicate relation between elements in the sentence. Parsing was formerly central to the teaching of grammar throughout the English-speaking world, and widely regarded as basic to the use and understanding of written language. However, the general teaching of such techniques is no longer current. Computational methods. In some machine translation and natural language processing systems, written texts in human languages are parsed by computer programs. Human sentences are not easily parsed by programs, as there is substantial ambiguity in the structure of human language, whose usage is to convey meaning or semantics amongst a potentially unlimited range of possibilities, but only some of which are germane to the particular case. So an utterance "man bites dog" versus "dog bites man" is definite on one detail, but in another language might appear as "man dog bites," with a reliance on the larger context to distinguish between those two possibilities, if indeed that difference was of concern. It is difficult to prepare formal rules to describe informal behavior, even though it is clear that some rules are being followed. In order to parse natural language data, researchers must first agree on the grammar to be used. The choice of syntax is affected by both linguistic and computational concerns. For instance, some parsing systems use lexical functional grammar, but in general, parsing for grammars of this type is known to be NP-complete. Head-driven phrase structure grammar is another linguistic formalism which has been popular in the parsing community, but other research efforts have focused on less complex formalisms, such as the one used in the Pentree Bank. Shallow parsing aims to find only the boundaries of major constituents, such as noun phrases. Another popular strategy for avoiding linguistic controversy is dependency grammar parsing. Most modern parsers are at least. This approach allows the system to gather information about the frequency with which various constructions occur in specific contexts. See machine learning. Approaches which have been used include straightforward PCFGs, probabilistic context-free grammars, maximum entropy, and neural nets. Most of the more successful systems use lexical statistics, that is, they consider the identities of the words involved, as well as their part of speech. However, such systems are vulnerable to overfitting and require some kind of smoothing to be effective. Parsing algorithms for natural language cannot rely on the grammar having nice properties, as with manually designed grammars for programming languages. As mentioned earlier, some grammar formalisms are very difficult to parse computationally. In general, even if the desired structure is not context-free, some kind of context-free approximation to the grammar is used to perform a first pass. Algorithms which use context-free grammars often rely on some variant of the CYK algorithm, usually with some heuristic to prune away unlikely analyses to save time. See chart parsing. However, some systems trade speed for accuracy using, e.g., linear time versions of the shift-reduce algorithm. A somewhat recent development has been parse re-ranking, in which the parser proposes some large number of analyses, and a more complex system selects the best option. Semantic parsers convert texts into representations of their meanings. Psycholinguistics. In psycholinguistics, parsing involves not just the assignment of words to categories, formation of ontological insights, but the evaluation of the meaning of a sentence according to the rules of syntax drawn by inferences made from each word in the sentence, known as connotation. This normally occurs as words are being heard or read. Consequently, psycholinguistic models of parsing are of necessity incremental, meaning that they build up an interpretation as the sentence is being processed, which is normally expressed in terms of a partial syntactic structure. Creation of initially wrong structures occurs when interpreting garden path sentences. Discourse analysis. Discourse analysis examines ways to analyze language use and semiotic events. Persuasive language may be called rhetoric. Computer languages. Parser. A parser is a software component that takes input data, frequently text, and builds a data structure, often some kind of parse tree, abstract syntax tree, or other hierarchical structure, giving a structural representation of the input while checking for correct syntax. The parsing may be preceded or followed by other steps, or these may be combined into a single step. The parser is often preceded by a separate lexical analyzer, which creates tokens from the sequence of input characters. Alternatively, these can be combined in scannerless parsing. Parsers may be programmed by hand or may be automatically or semi-automatically generated by a parser generator. Parsing is complementary to templating, which produces formatted output. These may be applied to different domains, but often appear together, such as the scan/print pair, or the input front-end parsing and output back-end code generation stages of a compiler. The input to a parser is often text in some computer language, but may also be text in a natural language or less structured textual data, in which case generally only certain parts of the text are extracted, rather than a parse tree being constructed. Parsers range from very simple functions such as scanf. An important class of simple parsing is done using regular expressions, in which a group of regular expressions defines a regular language and a regular expression engine automatically generating a parser for that language, allowing pattern matching and extraction of text. In other contexts, regular expressions are instead used prior to parsing as the lexing step, whose output is then used by the parser. The use of parsers varies by input. In the case of data languages, a parser is often found as the file reading facility of a program, such as reading in HTML or XML text. These examples are markup languages. In the case of programming languages, a parser is a component of a compiler or interpreter, which parses the source code of a computer programming language to create some form of internal representation. The parser is a key step in the compiler frontend. Programming languages tend to be specified in terms of a deterministic context free grammar because fast and efficient parsers can be written for them. For compilers, the parsing itself can be done in one pass or multiple passes. See one-pass compiler and multi-pass compiler. The implied disadvantages of a one-pass compiler can largely be overcome by adding fix-ups, where provision is made for code relocation during the forward pass, and the fix-ups are applied backwards when the current program segment has been recognized as having been completed. An example where such a fix-up mechanism would be useful would be a forward goto statement where the target of the goto is unknown until the program segment is completed. In this case, the application of the fix-up would be delayed until the target of the goto was recognized. Conversely, a backward goto does not require a fix-up, as the location will already be known. Context-free grammars are limited in the extent to which they can express all of the requirements of a language. Informally, the reason is that the memory of such a language is limited. The grammar cannot remember the presence of a construct over an arbitrarily long input. This is necessary for a language in which, for example, a name must be declared before it may be referenced. More powerful grammars that can express this constraint, however, cannot be parsed efficiently. Thus, it is a common strategy to create a relaxed parser for a context-free grammar which accepts a superset of the desired language constructs, that is, it accepts some invalid constructs. Later, the unwanted constructs can be filtered out at the semantic analysis, contextual analysis step. For example, in Python the following is syntactically valid code. The following code, however, is syntactically valid in terms of the context-free grammar, yielding a syntax tree with the same structure as the previous, but violates the semantic rule requiring variables to be initialized before use. Overview of process. The following example demonstrates the common case of parsing a computer language with two levels of grammar, lexical and syntactic. The first stage is the token generation, or lexical analysis, by which the input character stream is split into meaningful symbols defined by a grammar of regular expressions. For example, a calculator program would look at an input such as 12 asterisk 3 plus 4 2 and split it into the tokens 12 asterisk 3 plus 4 2, each of which is a meaningful symbol in the context of an arithmetic expression. The lexer would contain rules to tell it that the characters asterisk plus and mark the start of a new token, so meaningless tokens like 12 asterisk or 3 will not be generated. The next stage is parsing or syntactic analysis, which is checking that the tokens form an allowable expression. This is usually done with reference to a context-free grammar which recursively defines components that can make up an expression and the order in which they must appear. However, not all rules defining programming languages can be expressed by context-free grammars alone, for example, type validity and proper declaration of identifiers. These rules can be formally expressed with attribute grammars. The final phase is semantic parsing or analysis, which is working out the implications of the expression just validated and taking the appropriate action. In the case of a calculator or interpreter, the action is to evaluate the expression or program. A compiler, on the other hand, would generate some kind of code. Attribute grammars can also be used to define these actions. Types of parsers. Parser development software. Some of the well-known parser development tools include the following. Lookahead. Lookahead establishes the maximum incoming tokens that a parser can use to decide which rule it should use. Lookahead is especially relevant to LLR and LLR parsers, where it is often explicitly indicated by affixing the lookahead to the algorithm name in parentheses, such as LALROAM. Most programming languages, the primary target of parsers, are carefully defined in such a way that a parser with limited lookahead, typically one, can parse them, because parsers with limited lookahead are often more efficient. One important change to this trend came in 1990 when Terence Parr created Antler for his PhD thesis, a parser generator for efficient LLK parsers, where k is any fixed value. LR parsers typically have only a few actions after seeing each token. They are add this token to the stack for later reduction, reduce pop tokens from the stack, and form a syntactic construct, and error no known rule applies or conflict does not know whether to shift or reduce. Look ahead has two advantages. It helps the parser take the correct action in case of conflicts. For example, parsing if statement in the case of an else clause. It eliminates many duplicate states and eases the burden of an extra stack. A C language non-look-ahead parser will have around 10,000 states. A look-ahead parser will have around 300 states. Example: parsing the expression 1 plus 2 asterisk 3. Most programming languages, except for a few such as APL and Smalltalk and algebraic formulas, give higher precedence to multiplication than addition, in which case the correct interpretation of the example above is 1 plus 2 asterisk 3. Note that rule for above is a semantic rule. It is possible to rewrite the grammar to incorporate this into the syntax. However, not all such rules can be translated into syntax. Simple non-look-ahead parser actions initially input equals 1 plus 2 asterisk 3. Shift 1 onto stack from input in anticipation of rule of 3. Input equals plus 2 asterisk 3 stack equals 1 is 1 reduces 1 to expression E based on rule of 3. Stack equals E. Shift plus onto stack from input in anticipation of rule Leon. Input equals 2 asterisk 3 stack equals E plus hulls E plus hulls E plus. Shift 2 onto stack from input in anticipation of rule of 3. Input equals asterisk 3 stack equals E plus 2. Reduce stack element 2 to expression E based on rule of 3. Stack equals E plus 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 E is A E. Reduce stack items E plus E and new input E to E based on rule Leon. Stack equals E. Shift asterisk onto stack from input in anticipation of roulette wall. Input equals 3 stack equals E asterisks, asterisks. Shift 3 onto stack from input in anticipation of rule of 3. Input equals empty stack equals E asterisk 3. Reduce stack element 3 to expression E based on rule of 3. Stack equals E asterisk 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 E asterisk. Reduce stack items E asterisk E and new input E to E based on roulette wall. Stack equals E the parse tree, and resulting code from it is not correct according to language semantic. To correctly parse without look ahead, there are 3 solutions. The user has to enclose expressions within parentheses. This often is not a viable solution. The parser needs to have more logic to backtrack and retry whenever a rule is violated or not complete. The similar method is followed in LL parsers. Alternatively, the parser or grammar needs to have extra logic to delay reduction and reduce only when it is absolutely sure which rule to reduce first. This method is used in LR parsers. This correctly parses the expression but with many more states and increased stack depth. Look-ahead parser actions shift 1 onto stack on input 1 in anticipation of rule of 3. It does not reduce immediately. Reduce stack item 1 to simple expression on input plus based on rule of 3. The look-ahead is plus, so we are on path to E plus, so we can reduce the stack to E. Shift plus onto stack on input plus in anticipation of rule Leon. Shift 2 onto stack on input 2 in anticipation of rule of 3. Reduce stack item 2 to expression on input asterisk based on rule of 3. The look-ahead asterisk expects only E before it. Now stack has E plus E and still the input is asterisk. It has two choices now, either to shift based on rouletto or reduction based on rouleau. Since asterisk has higher precedence than plus based on roulefer, we shift asterisk onto stack in anticipation of rouletto. Shift 3 onto stack on input 3 in anticipation of roulette 3. Reduce stack item 3 to expression after seeing end of input based on roulette 3. Reduce stack items E asterisk E to E based on rouletto. Reduce stack items E plus E to E based on rouleau. The parse tree generated is correct and simply more efficient than non-look-ahead parsers. This is the strategy followed in Lalor parsers.